An important thing to consider is how to reduce the error in the finite element solution. To be able to understand that, let's go back to a slide that I showed earlier. And I talked about how one can go from a boundary value problem to a system of algebraic equations in nodal temperatures using the piecewise polynomial approximation for the temperature. So this is our assumed shape. In our case, we assumed it as as a combination of linear polynomials. And in the process of going from the differential equation to the algebraic equations, we introduce an error called the discretization error. And we can reduce the discretization error by improving our piecewise polynomial approximation. So how do we improve the polynomial approximation? There are two ways to do this. First is to increase the number of elements, and this I think is intuitive. In our original mesh, we had 3 elements, and then we can generate a refined mesh where we have 6 elements. In our original mesh, we had, so we assume the shape is a combination of 3 linear polynomials. Now we are assuming that it's a combination of 6 linear polynomials, and that's better. The other way to improve the polynomial approximation is perhaps less apparent, which is to increase the order of the polynomial within each element. And you do that by using more nodes per element. Here I've shown a mesh with 2 second-order elements. Okay, so this would be the first element, and that would be the second element. And each element has 3 nodes. Okay, 1, 2, 3, as opposed to here where each element has only 2 nodes. And when I have 3 nodes, I can write a quadratic approximation or a quadratic interpolation between these 3 values, as opposed to here where I can only write a linear approximation, connecting 2 values. And we'll see the effect of going to the second order polynomial. So here are the results I got with refining the mesh and also increasing the increasing the order of the polynomial. This was our original solution with 3 elements, linear elements. This is the solution with 6 linear elements, okay? And you can see that it's better than with 3 linear elements. So now I have 1, 2, 3, 4, 5, 6 linear polynomial segments. And particularly you can see that the derivative here, or the slope, matches better than over here. And we know that derivative is very important because it's related to the flux. And then I'm also showing you the result with a second order polynomial with just 1 element. Okay, so this is 1 element with 3 nodes. And I have quadratic, shape in between in that element. And this is a special case where the assumed shape matches the actual shape exactly. And if that's the case, the finite element will, boom, it'll match it, it'll give you the right values. And here, with 1 element, there's no difference between the exact solution and the finite element solution when you go to the second order interpolation. In general, the second order interpolation is very effective, and here it's probably not as dramatic as over here, but it's very effective. And when we go into ansys, we will see that in almost all cases the solver puts in the mid-side nodes and uses a second order polynomial rather than a first order polynomial. So then, if that's the case, what we need to do to get a better polynomial approximation is to use more elements. But we'll go and check, the order of the polynomial in one of the first cases. In fact, you will have an exercise where you're looking at doing the solution in ansys using linear polynomials versus quadratic polynomials.